So suppose you want to build a better pop can, one that minimizes the amount of material that you're going to use to construct that can. Now we want it to contain 20 or 12 ounces. That turns out to be, if you leave a little space for air at the top, the 12 fluid ounces is about 22 cubic inches. So that's kind of the constraint on this. But other than that, there's really not much of a constraint. So here's our wonderful picture. We can call that Jeff's Beer or Sigma Pale Ale. I don't know, Sigma Pale Ale sounds kind of at least vaguely mathematical. Pale Ale. Nice. Now, if you're minimizing the surface area, then there's a couple things to think about. Surface area has two parts. It has two lids, top and the bottom, plus the area of the sides. So maybe I should label my picture a little bit more. I'm going to draw in a radius, R, and a height, H. Okay. The two lids. Well, what's the area of one lid? Well, that's the area of a circle, right? The area of a circle is pi r squared. So we get a 2 pi r squared. Now the area of the sides is going to be a little bit more difficult to kind of fathom. So let's take a look at our can of beer. There we go, Sigma Pale Ale. And what I'm going to do is I'm going to cut this along the seam and unfold it. So what happens to this? Well, it just becomes a rectangle, right? And so I'm going to calculate the area of a rectangle. So let's do that. So it's going to be plus the area of a rectangle. What's the area of a rectangle? So we're keeping this simple. We're not trying to hit a home run right away, right? We're going to simple length times width. 2 pi r squared plus, we'll just do length times width. Now one of those dimensions is my h here, but the other dimension is that distance around the can. Now what's that distance around that can called?
Circumference.
The circumference. So I got 2 pi r squared plus the circumference, which is 2 pi r, times the height. And that's looking pretty good, except for one typical problem that we run into a lot of these things. It's got two variables, right? We can only have one variable. But there is something we haven't used yet, and that is that the volume is 22 cubic inches. Now, how do you get the volume of a can? Well, the fancy word for this is a right circular cylinder or whatever, but the volume is going to be the area of the bottom, which is pi r squared, times the height. And the cool thing is that I know that that volume is 22 cubic inches. I'm using cubic inches rather than fluid ounces, so that way this isn't going to be in linear units. So let's solve that over here. 22 equals pi r squared h. If I divide both sides by pi r squared, I get 22 over pi r squared equals h. Okay, great. Now let's plug that in right here. And now I've got a formula for the surface area that at least depends on one variable. So we'll call it S of R is going to be 2 pi r squared plus 2 pi r times 22 over pi r squared. Probably not a bad idea to simplify this. So let's do that. 2 pi r squared, 2 times 22 is going to be 44. Pi will cancel out, and one of the r's will cancel out, so it's going to be 44 over r. And I'll probably take care to write this one more time. 2 pi r squared plus 44r to the negative first power. Why do you suppose I'm writing it as r to the negative first? Yeah, just with an I ahead of things. Eventually I'm going to differentiate this, and it's going to be easier to do this here with our rules for kind of like polynomial type terms as opposed to the quotient rule. So looking at that. Let's think about our interval. Are there any natural restrictions on our interval? Zero. Yeah, that's kind of the only natural restriction. You can't have a radius of 0. You can have a radius as big as you want, although at some point your can would be vanishingly small and wouldn't be very practical. So, but somewhere between here and here, there's going to be a winner. So let's take a look at our function. So this is our analysis part. We've got S of r is 2 pi r squared plus 44r to the negative first. And, well, our only trick in the book at this point is to take the derivative. So that's going to be 4 pi r minus 44r to the negative second. Okay, so I want to figure out what's going on with that and where it equals 0. Because where it equals 0 is going to be a critical point. And we might find a minimum or maximum at that critical point. So let me rewrite this as 4 pi r minus 44 over r squared equals 0. Looks kind of ugly. It is kind of ugly. But I notice I got an r squared here in the denominator. There's no denominator here you can think of as being over 1. But maybe I want to clear out the denominators, because solving problems with you have stuff in the numerator, stuff in the denominator is kind of a pain. Suggestions. What can I do to clean this up?
Both sides by r squared.
Perfect. Let's multiply both sides by r squared. R squared times this is going to give me 4 pi r cubed. When I multiply r squared times this, I get minus 44. R squared times 0, of course, is 0. So now let's move things around. That's 4 pi r cubed equals 44. R cubed equals 44 over 4 pi, or 11 over pi. How do you solve? Yeah, cube root. R equals the cube root of 11 over pi. Nice. Now that's going to give you the radius. If you want to find the height, then you've got to plug it back into this equation up here. And there was kind of a surprise for me when I first solved this problem. And we'll see if it surprises you. Let's see. So I'm going to just plug this in numerically. I want to first calculate my value of r. So let's clear this up here. That's going to be the cube root. You can find that underneath the math menu, option 4. Cube root of 11 divided by pi. Exit that. Let's hit the store key, because that's kind of a pain of a number to plug in. Now that's the radius. I want to find the height, and then I also want to find the diameter. If this is the radius, how do I find the diameter? Times by 2. So that's the radius. Here's the diameter. Okay, let's see about finding the height. So to get the height, we're going to go back to this equation right here. 22 over pi r squared. See, this is why we saved it in our, store it in our calculator, because that's just kind of a pain to type in. So 22 divided by parentheses pi and then x squared. Is there anything about that result that surprises you?
It's the same as the diameter?
Yeah, it's the same as the diameter. So the diameter and the height are the same. Basically, you've got a square looking can. And years ago, one of my neighbor friends actually built me that can. This is the one that I passed around a little bit ago. But yeah, it's square. So that would be the one that minimizes the amount of material that you would use in constructing that. You can and perhaps should investigate this point with either the first derivative test or the second derivative test to make sure that that's actually a minimum point. But beyond that, no, I think we nailed it. It's kind of cool. Next time you're in the grocery store and you go down the vegetable aisle, take a look at some of the cans. You will see cans that have that dimension, that are just as tall as they are wide. And they're doing that precisely because of this calculus problem. They're minimizing the amount of material that they use there. So, cool.
Real life, baby.